In this lecture, we're going to go over some basic properties of measures. So first of all, let's talk about from the simplest one. So it satisfies the monotonicity. So it's basically saying measures are monotone. What do I mean by that? Suppose you have two elements, E and F, measurable sets. And suppose you have E is contained in F. Well, then the conclusion is that the measure of the set E is going to be bounded above by the measure of F. Okay, so in other words, when the set is monotone, so E and F, E is a smaller set here, the measure is also monotone. So the mu of this E, the measure of this E is also smaller. So the proof is really simple. Well, here the mu of F. Well, how can we break mu of F? Well, we know F can be realized as the union of two things. It can be realized as the E or the F take away E. All right, so here is the set F, and you have a set E, and you have the F take away E. Because E is contained in there, F is equals to the union of these two sets. And from our properties of sigma algebras, we know this set difference F take away E is measurable. So E and F take away E are disjoint and they're both measurable. So by the sigma additivity, well, we're really using a finite two of them. So this is the measure of the sum of these two. So you have mu of E and mu of F take away E. And whatever this mu of F take away E is, well, you know, is going to be non-negative because we're talking about positive measure right now. So in any case, you're adding something non-negative on mu of E, so this is certainly at least mu of E. All right, so this is the monotonic property. Well, the second one is called sigma subadditivity. So this is a quite important one. So let's let the following. So if I have a collection of En, so n going from 1 to infinity, they're both inside B. And let's consider the following. So the subadditivity want to say what is this measure of the union of these En compared to the summation n going from 1 to infinity of mu of this En. All right. Well, if En are disjoint, you know that the union is going to be equal to the summation. That's just sigma additivity. Well, now if I don't assume En to be disjoint, then what can I have? Well, when you take the union of these En may have some overlap. So when you kind of do the summation on the right of these En, when you add these En up, all these kind of overlap get double counted. So the right-hand side ideally is something bigger. So subadditivity is saying, well, the mu of the union is bounded above by this summation. All right. So let's prove this. All right. So here is the proof. And recall from when we talk about the sigma algebra, we say, well, there is a trick we're going to use very soon. That is, we write a countable union into a countable disjoint union. So if you recall, this union of n going from 1 to infinity of this En can be written as a disjoint union of An, all right, where An are disjoint. Right? And in fact, we have a definition of these An. Well, An is in fact just En, and you take everything that's inside the first n minus 1 of these Eis. All right. All right. So because this mu of these n going from 1 to infinity of En, well, we can because we wrote it as a different collection, so they're the same by definition, we're measuring the same set. And now the AN are disjoint, we can use the sigma additivity. So this is the summation of mu of these AN and going from 1 to infinity. This is by sigma additivity. Sigma additivity. All right, so now each of these mu of AN is a subset of EN because it's EN take away something. So here, that will imply AN is a subset of EN. And because AN is a subset of EN, by the monotonicity, we know that measure of this AN is bounded above by this EN. So each of these mu of AN, so here the mu of AN will be bounded above by mu of EN. Okay, so we just prove this property. So as a result, when you're adding something smaller on each term and you add them up, the infinite sum will be also smaller. So this is summation of mu of En. All right. So if you combine them together, now you have mu of this union of En is bounded above by the summation of mu of En. So the idea is when E are disjoint, again, when E are disjoint, the right-hand side may double count some overlap among En, while the left-hand side doesn't. All right, so that's why the right-hand side is strictly bigger. So here, I'll just do a quick note here. I know you are reading also the course note. So if I just assume it to be, if I don't take an infinite union, so this property mu of union n going from 1 to say some big N of En, well, of course, you run the same argument. This is less than equals to the finite sum n going from 1 to n of mu of En. So you can show all the measure will also satisfy this. Well, this is called the subadditivity property. All right, so this is the subadditivity. So when we say sigma subadditivity, we usually mean there has to be an infinite union. All right, so this is a slight difference from the course note. Anyways, let's continue. So the third property I like to go over is something we call the continuity from below. So what do I mean by that? Is that suppose you have a bunch of sets, say E1 containing E2. So you have a chain of subsets, an increasing chain of subsets. Then the measure of this union, so union n going from 1 to infinity of this En, kind of like the limit of this chain. Well, this is continuous kind of, so this is equal to the limit of the measure of actually the En. All right. All right, so how do we prove this? Well, the proof is fairly simple. So I want to show actually a slightly more general argument. So let's make the following claim, which is more general. So suppose I let I have some collection Fn and going from 1 to infinity, and that's collection of sets in the sigma algebra. I don't require them to be a increasing chain, but we'll show how we get the increasing chain later on. But anyway, so I want to claim the following. I want to claim that the measure of the union n going from 1 to infinity of these Fn, okay, so this is going to be the limit of n going from infinity of the measure of the finite union. So I should use a different letter here. Let's say k going from 1 to k going from infinity, where I'm taking the finite union from n going from 1 to k. So I take the first k of them, all right, and then I measure them. So I let k goes to infinity, so I'm measuring more and more union. then this limit will converge to the union, the countable union of these Fn. All right. So here's a proof. Again, the idea is that we write this countable union of potentially non-disjoint sets as a disjoint union. All right. So I do it where An are disjoint. All right, so if you recall from our previous lecture, when we did this procedure of decomposing this potentially non-disjoint union into a disjoint union, then we show that the following happens. So we have this definition. So An is essentially Fn, take away all the first n minus 1 of them. And we actually show the n going from 1 to k of these Fn. That's the same as the first k of these Ans. So the union of the first kf is equals to the union of first k of these Ans. All right, so now what do we have? Well, the measure of this union, so measure of union 1 going from n going from 1 to infinity of these Fn. Well, by definition, this union is, we can rewrite it as a disjoint union of these An. An, they're disjoint, so by the sigma additivity, we know is the infinite sum of mu of these An. So this is by the sigma additivity. All right, so what is this infinite sum? Well, by definition, the infinite sum is just the limit of the partial sums. So this is, let's do the kth partial sum of these mu of An. All right, so this is just definition of this infinite sum. Well, the first k partial sum, well, because again An are disjoint, this is the mu of the union n going from 1 to k of these An. Okay, so this is just, you can say this is by sigma additivity, or basically additivity, or using a weaker one than the sigma additivity. But in any case, we show that the first k of these An, when we take their union, is the same as the union of the first k of these Fn's. Okay, so they're the same. So we just proved our desired result. So this the mu of this union is equals to the limit of mu of these finite unions. All right. Well, now to show that, what do we want to show? Well, we want to show this continues from below. Well, if you have an increasing chain of these ENs, so here EN is an increasing chain, you want to show that the union is the limit of EN. Well, now based on our claim, this is fairly simple to show. So now suppose I have E1 contained in E2 and so on. Well, what do we show? Well, we can show that the union of these En, well, we just show that this is the limit of the first finite union, so the first k finite union, and that k goes to infinity. And because En are increasing, so you're taking the union of a bunch of increasing subsets, so you have E1 here, and then you union E2, which is where E1 is containing E2, so their union is just E2, and then you union E3, which is E1, E2 all containing E3, so you get E3. So you can convince yourself this is simply the first union, the first k union is just equals to ek. So this is limit when k goes to infinity, mu of ek. All right, so this proves our desired formula. All right, so the last property, I will just write it down. So this is called continuity from above. you can do it with a decreasing chain, all right? So suppose you have E1 is contains E2 and contains E3 and so on, all right? And let's assume the first one, the mu of E1 is less than infinity. So I need the first one to be a finite measure, all right? Then what we can conclude is that the mu, if I consider their intersection, so it's if you think about you take the intersection of all of them, it's more like the limit of this decreasing chain. So if you take the intersection of all these En, right, then this is going to be equals to the limit when n goes to infinity of mu of En. All right. So I'm not going to prove this one, so this one will leave an exercise. I'll put it on your assignment. Okay, so C assignment. The second assignment. And you should also convince yourself this condition where I require the first one, the mu of E1 less than infinity, that is really necessary. That's going to be a question on the assignment as well.